on their license so I can access it. They got Javed on it.
Yeah, why? Now we are on the record. But there are no secrets. Keep talking.
Okay. So I just have to get the guy to add me.
So you want to still do more?
No.
By the way, I emailed that guy and that guy replied to my email. I didn't get a reply of you email. You remember you emailed them?
Yeah, I believe I replied to the automatic.
There are the license bars in
What?
Okay.
Do I need to hide again?
Huh?
Do I need to hide?
Can you? Oh, yes, you can.
I can.
Okay. Next time I will. No, I cannot promise, but I have intention to bring a tripod to make it a little. It goes so slow. Okay.
Oh.
Which just doesn't work.
So do you have a new gel that?
So you got a chance to enjoy this. To enjoy this. To enjoy this biological symbols, I'm going to erase them. Sorry, but they are already recorded. If you need them so much. So who we are and what we are doing.
We're lazy.
Yes, yes, definitely. I'm with you on this.
So we're trying to approximate the two Hamiltonian with a solvable Hamiltonian and an perturbation.
No, it takes so long to turn it around. I better.
You need a Daisy Duke.
What is it?
Is that the thing that you can spin easy? You put on the table?
So, how did you tell? You want to avoid to do what?
Diagonalizing a matrix.
We cannot diagonalize the matrix.
So
No. If the matrix is time dependent, diagonalizing it is not a good task. Well, if you hate someone, you can ask him or her to diagonalize it. But we do want to solve time-dependent problems. We keep in mind oscillatory, sinusoidal, like harmonic perturbations. So the Hamiltonian is time-dependent, right? So what should we be interested to do? This one is much easier than. Uh-huh. Well,
No.
no. Better? Yes. I do not want to be on the spot for the whole time. So we already got some equations in the class, right? They give us expansion coefficients of wave function if the Hamiltonian is time dependent, and we want to plot them and see how they look like, right? How do we know? How will we know that the solutions are good or bad? Yes, yes. You are done for today.
Yes.
But what is the exact solution in the time-dependent problem? How do we get it? Huh?
You said I was done. I can't answer once I'm done.
You can help your classmates. Brendan, you got help. How do you get exact solution?
Was it good help or okay? Time evolution operator.
Yeah. So what is our plan? What would you make the? How would you design the plan if you would plan this lab? Release everyone home. But any other plans? We'll go through the text of the code. Do not worry about it right now. Let's just discuss.
Vary different parameters and see how that affects the result.
Yes. So we need two solutions, one exact and one approximate. And then we need to compare them. Since they are time dependent, we need to decide at which time step we will compare them. And then, as you've told, we need to compare these two solutions as function of some parameters. And probably we can repeat the same idea as we did previous time. We set up tolerance limit, like 1%, and then we see how far we can tweak the parameters and stay within 1% error. Approve as a plan? Okay. Good. So we do have Hamiltonian as 0 plus perturbed, which is function of time, and we are thinking that it is some parameter times cosine omega t. So something is, this could be an operator. And then we look how does this Hamiltonian affect the wave function. Right?
That's not low, right? That's low inside.
This is my calligraphy for the letter phi. P-H-I, if you are in LaTeX. And I wouldn't try to pronounce it. Or I can try. How do you pronounce it? Phi or phi? Okay, good.
No,
Huh?
that's not fee.
Phi?
Is it?
It should be fee. It has an I. Big I.
Phi?
No. I.
Native Greeks probably would pronounce it like phi. I don't know. We should invite someone who has an idea how to pronounce it. Okay, doesn't matter. We are going to have example of two-level system, because otherwise it will be too long. And then we will assume initial condition that at time equals 0, C1 equals 1, and C2 equals 0. Right? So then we are doing first order perturbation theory, which means that the solution will be a summation of zeroth order solution plus something. So solution for C1 will be zeroth order plus 0 because there is no correction to this orbital in the first order, and for C2 there will be nothing because we did set up it as initial condition plus C2 first order correction as function of t. So the first coefficient will be always 1, and second will be equal to C2, right? Our observable to compare will be the occupation of the excited state. So look for C2 star C2 of t. And we will have this observable in two forms. P exact, actually in three. P perturbative and PT first order and PT resonance.
So why don't we don't have to normalize it?
We can normalize, and it will be smart if we need to model real processes. But then, since you suggested it, it will be Levi perturbation theory or Lustrom perturbation theory. In the regular one, it is not normalization is not included into procedure.
We have to bring Greg in it because he always said that our wave function has to be normalized, so that's why I asked.
But it is not normalized, and the probability will not conserve with perturbational solution. This one, the resonance one, will be constant times t squared, right? And it will experience unlimited growth very soon. So do not trust perturbation theory on long times. So why do we do exact and two brands of perturbational?
One is real easy.
Yes, because if we assume the resonance condition, the exciting frequency is in resonance with transition energy, then the solution will look this way. And this coefficient alpha will be something like our strength of this interaction squared divided by 4 is bar. That's it. Here is the solution. Okay? In class, we were considering atom or whatever molecule in the electric field, and this V was product of transition dipole moment matrix element and electric field strength. This one will be coming from C to 1 of T to H, and here there will be exponential of two terms which contain the different formulation, different accumulation of phase in respect to frequency of the incident value. Maybe it was not the smart way to hide it under the printer. It's not.
Is the omega minus?
One in first minus, in second plus.
And then the denominator is it minus plus?
Same as in the denominator. Here is our range for showing equations. Here is plus. And then this expansion coefficient is plugged into such expression, and then we get this simple observable. And the exact obtained with evolution operator is what we discussed last time, right? So,
it's lost in the code.
huh? What?
It's lost in the code.
Yes. So Levi told us that reason for resonance solution is because it is simple and easy to analyze. Why don't we stay with resonance solution only? Huh?
It's bad after a short time.
Well, this is bad after short time either. We will see. But here we can, the perturbation theory is not limited to resonance case. If some of you did express curiosity, what will happen if if this resonance condition is not satisfied, if we are in the offset between incident light and the energy levels, then this expression is good. So we can also scan over different values of perturbation frequency to make it a little higher or lower frequency and see what will be the consequences. So, we will plot on the same plot, we will show on the same plot exact perturbative with offset and perturbative resonance as function of time, right? And we can do it once, then change parameters, run once again. So which parameters can we change in order to explore the coincidence of those things, of these solutions? So we can change we can change V. What else?
Omega.
We can change omega. And we can select time for comparison. It is expected that if you select very early times, then everything should coincide, to be very close. If you select long times, then things should be different. Anything else we can change here? Probably not. Also, in selecting time to comparison, what would be the smart choice? Intuitively. Because if intuitively we expect that under, and we have already seen exact solution, under the strong resonance perturbation, the population of these orbitals will start to oscillate up and down, up and down. So the pace of the scaling depends on this V. So probably we should select this comparison time as like 2 pi over V, or maybe 2 pi over V divided by 10 or by 4, like quarter period of this oscillation. Maybe, it's just suggestion. Okay, so how do we build the code? We do not build it, we use pre-made code.
Can we change the energies?
We can change, well, if you want to practice spectroscopy under laser with constant wavelengths, yes, you take one exciting frequency and then plug in different molecules. But it is more reasonable to take molecule whatever levels are, and then yes, we should record it for sure.
Hey, it looks like polarized
Yes,
light.
it is an illustration of, of a wave. Probably we can trim it.
That's cool.
It's the best thing we ever did in the class. The rest is garbage.
I only ask because when I make the difference large, it looks as if the first order perturbation agrees with exact at a much better degree.
Can you make V large?
No, delta E. So on line 8, if you change it from E2 to like if you change E2 to a larger number, it looks like it gets better.
But then you change, then the offset also depends on it. So you're changing omega when you change that.
But I think omega is a different omega than, no wait, it has to be the same.
Omega is offset, and it depends on W1, which depends on E2.
So then when,
So you can derive omega somehow, some different, something different.
How do you change font in MATLAB? Yeah, font size, yes.
oh, you did this last semester.
Yes, but I wiped off any memories from the brain.
If you go to, if you hit Command, comma, or if you go up to MATLAB and then down to Preferences, and then if you go to Fonts,
Preferences, yes. Excellent. Thank you. Okay, so what are we doing? Variables.
Looks like the way we have it set up, without changing anything, half an oscillation is the 200 seconds.
Well, if you want it to be applicable to true life, we may want to clean it up a little bit. If you set up h bar equals 1, then energies should be like 1 over 27 or 1 over 10 to be in the optical range. If you put energy 1 it will and set h bar equals 1, it will correspond that we are in the high UV. But in principle, it changes nothing. It is applicable in a wider range.
We could change on 11 we say an offset. We could also change that parameter.
Yes.
That's all my idea.
Yes.
No, that's
Here offset. So let's quickly go through the code. So we have initial condition. We have this energy of states, strengths of the interaction that will be coming in a harmonic way, and then we do have the frequency of the incident perturbation approximately equal to energy difference of levels plus this offset that we can set up, right? So if you want to stay away from the resonance, we need to make this number smaller. Bigger, correct.
So
then everything in the loop here from 4 to whatever to end, this is exact solution with evolution operator, which you see here, right? Show it. Yes, evolution operator. And later we do set up the perturbation theory solution. So you see this exponential with excuse me, difference and summation of the perturbation frequency and the energy offset, and then we just add them together. So it is the perturbation solution that we are saving in this variable. And then we can also set up the resonance solution, which is just linearly growing for expansion coefficient, and then if you take square, it will be quadratically growing. So for observable, we take this conjugate of wave functions to itself. So this P2 is exact solution. The perturbation theory P2 is perturbative with different values of offset, and then the resonance P2 is occupation of excited state under this resonant condition, and then we just plot them all together and see how they look like. So let's run and see what happens. So what do we see? What do we see here? Good. So first, you can observe the shortcoming of the perturbation theory. The upper line here is straight, which stands for perturbation solution for initially occupied state doesn't change. So it is 1, which is already 1. The exact solution is this blue line and this red line. So they the one that was initially populated drops, the one that was initially empty raises, and you see a little fringes. So these little oscillations here show the real scale of the perturbation. So we did select parameters in the range so that excuse me, this perturbation is a small fraction of energy difference in the absolute value, energy of perturbation. But you see this frequent oscillations, and the change of population is also, you see this little bigglings, it is modulated. Now, the perturbative solutions for first order with energy difference and resonance condition do coincide. So this, there are two black lines, but right now they coincide because we are really close to resonant condition. Right? And we see that up to about like quarter period, if you look forward, you will see that oscillations, the occupations will start oscillating. But at the early stage, the quadratically growing function is a good mimic of this behavior. So if you do, if you do change the duration of the simulation, here, like if you expand the number of steps, you see that exact solution oscillates, and the perturbative solution will never come back. Right? So we are in the regime where it's unapplicable. And there is an interesting feature. Well, there are several interesting features, and you discover them yourself. But let me ask a question, and then we will check what is the result. So answer without trying it. What do you expect from exact solution if we run with bigger offset? If the offset increases, what happens to exact solution? Huh? Qualitatively. Let's think together. So, off resonant excitation, the frequency of light doesn't match the transition energy of the molecule. If it is hugely off resonant, then who told nothing? Nothing, right? Then molecule will not get excited. But if it is a little bit closer to resonance, so what is the moderate intermediate case between oscillations and nothing? Do not try, just think.
Less oscillations.
You mean in frequency or in amplitude?
Oh, their amplitude is smaller.
Yes. So the state, the excited state, will never be populated to 1. But it will get like population maybe 10% or 50%. Now let's check it. Put the offset about 10% and see what will be the solution.
Yeah, we got to increase it. Okay, pull it down again.
So let's see on the exact, what happens to exact solution. See, before it was approaching 1, and now it is goes only to 50% population. If we increase the offset, in this will still oscillate. This excited state will still get some occupation, but it will be less than 50. It will be like 10%, 5%, so small oscillations. So even with off resonant light, you can create a little excitation, right?
How'd you get that? You said the offset's at 10%.
Let's go back to the, no, it's here. So I did place offset of 1%, and then just saved and rerun. See what happens if it is 10%, 0.1 of the energy difference. You see, it is very close to nothing. So if we 10% off resonant, there are very little weaklings of the decrement in the initial state and increase of the
What's your T stats?
T steps. I put it 4,000.
1,000?
4,000.
4,000, yes.
Try 0.5.
0.5. Oh, 0.5. 0.5 AC.
Do you see? There are some a little higher amplitude, but if you never create 100% occupation in the excited state.
So 0.01 never really goes. 0.01 only goes to about 80%. Even 0.05 doesn't really. Yeah, 001 goes to 100. Even 002 doesn't.
Okay. Oh,
Yeah, that's 001.
Mhm.
Yeah. And 002, that's almost there, but not quite.
so how would we evaluate the error? What are our options? Yes, but let me do it. If we subtract perturbative minus exact and then plot it,
does hold on mean?
It means every time you apply, it won't delete the last one.
Exactly. Yes. Yes. And if you want to opposite, to delete whatever was quoted, you can type hold off.
Can you do math inside the plot environment?
Hmm?
Can you do math inside the
What do
plot
you mean?
environment?
What do you mean math?
I want to plot exact minus perturbation inside the plot environment. Does plot, the function plot only take variables or does it take arguments as well?
You can
Like
put in like
in matlab.
t squared.
You can just like plot any function.
Or can I plot a sum of two functions? Or
You can. Yes.
You can. So you can do math in the plot.
Yes.
Okay.
Yes. I thought you were asking whether one can do labels with math symbols.
Oh, no, that's, I don't know.
Yeah, that means that it will ask when you can figure every time. I think you can, you want two. This one is separate. You can do a subplot and problem. Yeah, because when the code plots or whatever figure you have last touch, will plot on that figure. No, but then it will do that. And then here you do the last one and you say hold on. So you can do a subplot and have a first panel and a bottom panel. You know what I mean?
What is this plot?
This is red line here.
Oh, yeah, you want this.
Yeah, that's what you can do a subplot.
Subplot.
Yeah, we have to do that the first one as well. I think you can also say close figures. And that'll close out the figures so you have a new one or you can close out the figures.
Well, that's a whole lot. But that means
You know, hold off means that it won't sit, it will keep writing over it.
Okay, I got something. So the error is small at first and then exponentially grows.
That might be the resident one, not the first one.
So it's pretty much zero up here, but then it's sorry. So here it's base difference, what is difference, right?
Quadratically, because
So well, it's very it's really weird because it's very small. Then quadratically will go.
oh, because you're using look.
Yeah, but I changed, I added something because if you kind of normalize it, then the error looks much better. Like this is the original, but then I did 1.5 minus the sum of the third divided by 2, and then the error does not, it doesn't go up to 1.
So you designed your own perturbation theory.
I don't think so.
Well, or you can, if you are so humble, you can normalize, not name it not after your name, but like normalize perturbation theory.
Sure.
So let's make a scan of the offset parameter. So what I suggest we select to compare all solutions at a fixed time, maybe time step 100 or time step 500. And then repeat the calculation for like 100 times with different values of offset. Not manually, you can make a bigger loop that you repeat everything. Does it make sense or not yet?
I'm sorry.
Let's inspect how the error depends on the offset parameter. Where the error is bigger, near the resonance or far away from the resonance. For this purpose, we need to plot the error as function of the offset parameter. And we can do it automatically.
Oh yeah.
Good?
Yeah. Why do you plot v times dt? I plotted just dt and then the error.
Then the axes are more reasonable, not from 1 to 4,000, but from like 1 to 3, smaller numbers. Then we are using units.
What does your graph look like? Can you plot it?
So 0, 1, 2, 3, 4. But we can do it your way and just put TT as an argument.
Oh, where is your solution?
I plotted them separately, not.
Oh, okay. I'm plotting the error on top of the solution.
That's fine. So when we meet in class, I will try to formulate a homework, like what you can prepare and submit. But in brief, it would be some form of a question asking for error as function of offset parameter. So let's program it and plan on creating a nice figure as a homework, which we can complete all together now. So the idea is to establish another array which will store value of the error at a given time and accumulate this value for each value of the offset parameter. And we will, basically the whole script should be wrapped up by another loop. Make sense? Give me secret signs if it doesn't make sense. No? Okay.
Is there a way to, well, the problem is, do I integrate over the error for each offset?
Yes.
But
You can.
the bounds of the integral will have to be weird because
You can make summation, just SUM of the array. And you can set up, if you want to convert it into integration.
But the frequency of the solution depends on the offset. So then that's
if we will inspect just a point value at a given time, we can also see the delta function, the resonance function that will have peak, the one that you guys were drawing on the blackboard during the class. Mm-hmm. Yep. Well, let's do it only for the direct, but see how it looks like. And it is not just a peak. It will be a peak, and then the function will go to negative values, or not negative, but it will go to 0. If you go to wave function, it will go negative. If for occupation, it will go to 0, then up, then again to negative, and then this fringes will get less and less.
mine, I could say A equals 0.01 add 0.01 until 0.1.
Oh, I don't have to like actually do this.
No, because you're gonna add like you're gonna do it 10, right? So
From 0.01.
if this was not here, right?
The building map, then it doesn't.
Then it makes a difference. So you could leave it the way you had it, but then you divide it by 10.
That's what I was going to do. Oh, but if we can do it with some capsules.
You probably don't want to do that. I just no, the issue is the other source.
Well, you face consequences if it doesn't like it. We just complain, but previously it didn't.
You can start the loop right at the next step. Yeah, so I have offset and I pull that stuff line so that actually you know that no no actually no, it should be out. It should be the way you have it because
Right now, fine.
but we don't get our the initial conditions are not no longer reset every time.
Right.
So it should be about that. I think this huge capital D. What how many behind your error? You said an error there. And then how many add to it?
So that's like error, and then add your
No, that's outside of the loop.
It's
No.
supposed to be
No.
the offset first.
Yeah, it needs to be outside of first, but within the second. Doesn't it? Otherwise your array's not being built. It's up to the last loop. Right? But then
Where's EXP in
Your call will be disconnected.
so that has to do with your size. R. But then you don't find that. What's your dimensions? How do you set ET error? So that is a column arrays, right? If we look at the column, so that's going to go this way.
Here.
Yeah. I just did it right here. Your columns.
Like 1 by 4,000. Oh, we have to get that at time equal 100, for example. We have to get the error at time equal 100. That's right now we're having 4,000. Just 4,000 times this. And the error. He said you choose a time. Choose the error at that time. Right?
I think I was kind of sidetracked with my time.
So we need to get the time at every so P error. And how do you choose it? How do you choose it?
So you see this. So that says, I think, column and everything in that column.
Well, we just want one. We want a single value.
So then say like 1, 1. And I think that will be your top. And I don't remember which one.
So
But
Ah.
the frequency distribution depends on the offset. So we can't just choose certain time.
we have to.
No, I think what he was saying was we have to integrate the error curve.
But you have to integrate it, but the bounds of the integration will depend on the offset too. Because the frequency of the solution depends on the offset.
Why can't we just choose the time?
Like, okay, so look now, the error goes from 0 to some high value to 0 back to around 300.
Yeah.
So you change the offset, let's say, whatever, from
Right.
0.2 to 0.3. Oh, and then the error goes from goes to some maximum value, and then it goes back to 0 around 200. So if you integrate from 0 to 300 every time, then you're going to get some negative contribution to the error. That doesn't make sense.
Why,
Or you integrate over that.
why do error like zero?
Because it's
Also,
not
the error oscillates with the different
structure and construct.
We got disconnected from this.
But that's because we would the error that Dimitri had was the error of the resonance form, not the PT1.
So you gotta change the offset, find the bounds of the integration, integrate. At every time, at every offset value, you gotta find the bounds of integration.
But then that
Oh, so you're saying the blue one goes back down to 0. If you add them all up.
Do you have this red curve?
Yeah.
Or
No,
is it just-
I'm the same as one.
I do.
If you put hold on in front of the last one, and then you plot it.
And then it will make it a lot easier to see.
But then I don't want to do it now. Why? Remove what?